Welcome back. Just continuing this ultra 5-star problem, just so you make sure you understand everything that's going on, especially with tension and pulleys and all the rest. So here we figured out the net forces acting on this block, and we said it was the tension of the rope minus the force of friction, and we figured out the force of friction in the traditional way, and that equals the mass of the block times the acceleration of the block. And actually, it would have been a good idea here to solve for tension. So what is the tension pulling on this block? The tension is equal to 10 times the acceleration of the block plus 39.2 newtons. 39.2. And actually, this is probably the one that I should have squared, because this is even more useful than what I wrote before. So we figured out the tension of the rope here in terms of the acceleration of the block. And then we moved on to the pulley. And we said, okay, well, what are the net forces acting on here? We have 150 newtons to the right. And we have twice the tension pulling back, right? Because we have the tension here pulling back and the tension there. And that's kind of what pulleys do. And we knew that because the tension in the rope is constant. And if you were to do it here, not that it matters, the tension on the rope here is T. And then the wall is pulling back on the rope with the force T, and that's why this point is constant. But we don't have to worry about that. So back to the problem. So we said the net forces on the pulley, which is 150 minus 2 times the tension, is equal to the mass of the pulley, 5 kilograms, times the acceleration, and this is a P here, times the acceleration of the pulley. And at the very beginning of the problem, I had said, well, the acceleration of the pulley is half the acceleration of the block. And I went off about all the reasons, and I'll say it one more time, because if this pulley moves an inch to the right, not only will the pulley move an inch to the right, this length of wire will get an inch longer, right? Because this is stationary here. So this length of wire, since the wire is a constant length, will get an inch shorter. So this is getting an inch shorter, and the pulley is moving an inch to the right, so this block will move 2 inches to the right. So that's how we came to the conclusion that whatever the velocity to the right of this pulley is, the velocity of this block will be twice that, or whatever the acceleration of this pulley is to the right, the acceleration of this block will be twice that. And that's where we wrote here. The acceleration of the pulley, or the acceleration of the block, is twice the acceleration of the pulley, or the acceleration of the pulley is 1/2 the acceleration of the block. So with that said, we took this equation and we substituted the acceleration of the pulley, and we said, well, the acceleration of the pulley is just half the acceleration of the block. The pulley's velocity and its acceleration is half whatever the block's is. And so we substituted that in for the acceleration of the pulley. And now we can substitute tension, which we solved here, for the my mind's getting flustered, for the tension in this equation. So what do we get? We get 150. Let me move back to a nice color. 150 minus 2 times this expression. This is the tension in the rope. 10 times AB, acceleration of the block, plus 39.2 is equal to 5 times 1/2. Well, what's 5 times 1/2? It's 2.5 acceleration of the block. So we have 150 minus 20 times the acceleration of the block minus, what is this, 78.4 is equal to 2.5 times the acceleration of the block. Well, let's add 20 times the acceleration of the block to both sides. Well, we'll just simplify this. 150 minus 78.4. See, 150 minus 78.4 is equal to 71.6. So 150 minus 78.4 is 71.6. So that's just this minus this. And I'm going to add 20 AB to both sides. So I'm essentially moving this 20 AB over to that side. I'm skipping a couple of steps just to save space. So if I add 20 times the acceleration of the block, that's not AB, it's A sub B. You get 22.5 times the acceleration of the block. And this is a 6, not a block. Right? 71.6 is equal to 22.5 times the acceleration of the block. We're almost done. So we divide both sides by 22.5, and what do we get? Let's see, divided by 22.5, and we get the acceleration of the block. We get the acceleration of the block. So that's this block right here. Let's see, the acceleration of the block is 3.18 meters per second squared. meters per second squared. That's how fast this thing accelerates to the right. And we already figured out that the pulley accelerates at half that rate. So whatever that's that number divided by 2 is equal to. So the pulley itself, the acceleration of the pulley, is half of this number, which is 1.59 meters per second squared to the right. I know this was a fairly difficult problem, and the key realizations, though, I think that you had to discover or realize in order to be able to do this was a couple of things. One, that the acceleration of this pulley is half the acceleration of the block, or the acceleration of the block is double the acceleration of the pulley. You have to realize that, and then you just have to work out the net horizontal forces and realize, well, the only thing pulling on this block is friction going backwards and tension of the rope to the right. And that same tension of the rope is constant throughout this wire or through this rope. And on this pulley, and this might not be something that you had already realized about pulleys, but now you will, is that since the rope essentially goes around the pulley, it's pulling twice on the pulley. And the tension's constant, so it's pulling with the tension of T on the top and the bottom. And if you realize those things, then it's just a little bit of algebra to get the acceleration of the block and the acceleration of the pulley. Anyway, I hope I didn't confuse you too much. This is actually, I would call this a 5-star problem. If if you would see this type of problem on like physics competitions. So if you know how to do this, you're doing well, at least as far as tension and ropes and friction is concerned. I'll see you in the next video.